Hello everyone, my name is Tanush Reddy. I'm from second year of engineering from CSE Cybersecurity. Now I'm going to explain about concepts of K-maps. Here is the introduction to K-maps. It is also called as Karnaug's maps or K-maps are a graphical method used for simplifying Boolean expressions in digital logic circuits. This technique offers a visual and intuitive approach to finding the most efficient logic circuit representation for a given truth table, effectively reducing the number of gates needed for minimizing the overall complexity. Concepts of K-maps. The K-map are essentially a visual representation of a truth table. They are grid-like structure where each cell represents a unique combination of input variables. The arrangement of cells ensures that the adjacent cells differ by only one variable, allowing for this easy identification of groups once known as minterms. The key to K-map lies in grouping these adjacent ones by performing the largest possible rectangular groups of ones. Covering all ones, we can derive the simplified Boolean expression, eliminating unnecessary logic gates and minimizing the circuit's complexity. Variable agreements. Variable assignments. Each cell in a K-map corresponds to a specific combination of input variables for complex into variables like 0, 0, 0, 1, 1, 0, and 1, 1. The arrangement of cells ensures that the adjacent cells differ by only one variable, which is crucial for grouping ones. Grouping of ones. The primary goal is to group adjacent ones together in the largest possible rectangles. These rectangles must always be powers of 2 in size. The group size corresponding to number of variables involved in the simplified term. Boolean expression derivation. Once the groups are formed, the simplified Boolean expressions are derived by identifying the input variables that remain constant within each group. For example, a group covering 0, 0, 0, 1, and we also have the variable x as a constant 0, while the y would be the eliminated resulting and in a term like x complement. Advantages of K-maps: simplification, visual approach, minimization, and easy to use. Disadvantages of K-maps are limited to small number of variables, don't handle don't care conditions well, potential or applications of K-maps. K-maps are widely used in various aspects of digital logic design: simplification of Boolean functions, digital circuit design, logic circuit optimization, fault detection and diagnosis, education and teaching. Simplification of Boolean functions using K-maps. Truth table generation. Start by creating the truth table for the given Boolean function, listing all possible inputs combination and their corresponding outputs. K-map construction. Construct a K-map based on the number of input variables. Assign each cell to a unique input combination, ensuring adjacent cells differ by one variable. Grouping of ones. Identify the ones in the K-map and group them together the largest possible rectangles. These rectangles must always be powers of 2's in size. Expression derivation. For each grouping, identifying the input variables that remain constant within the group. These variables, along with their complements, will form the simplified terms in the final expression. Limitation of K-maps. Despite their usefulness, K-maps have limitations that restrict their applicability. Large number of variables. K-maps become unwieldy and impractical as the number of input variables increases. For circuits with more than 5 or 6 variables, K-maps are not feasible. Don't care conditions. While K-maps can handle don't care conditions, the optimization process might not always be as straightforward as with standard Boolean expressions. Error potential. Incorrect grouping of ones or misinterpretation of the K-map can lead to errors in the simplified expression, requiring careful attention to detail. Now, let us come to the conclusion. The Karnaugh maps are valuable tool for simplifying Boolean expressions and optimizing the digital circuits. Their visual presentation and straightforward approach make them accessible to designers to all levels. While they have limitations regarding the number of variables, potential errors, and their efficiency and simplicity make them an essential part of the digital logic design toolkit.